That's the sound of the crew coming back online after a 40-minute communication blackout with mission control during a period when they set their eyes on parts of the moon no human has seen before.
It is just fascinating here. It's so cool.
The more I look at the moon, the browner and browner it looks.
Little islands. There are islands of terrain out there that are completely surrounded by darkness.
For the first time in modern history, humans disappeared behind the moon, and Earth heard nothing. No signals, no updates, no backup, just silence. But this wasn't a mistake, it was planned. This mission wasn't just about flying past the moon, it was about testing what happens when astronauts are completely on their own. So what really happened during that hour of isolation? Why would NASA risk it? But what shocked the crew wasn't the silence, it was what they saw. Because the moon, up close, didn't look gray at all. It turned into something darker, almost brown, and far more unfamiliar than anyone expected. The most defining moment of this mission began the second the spacecraft slipped behind the moon. As Orion moved out of Earth's line of sight, communication instantly vanished, leaving the crew completely cut off. According to mission coverage and onboard recordings, this blackout lasted close to an hour, not because of failure, but because the moon itself physically blocked all signals. That moment transformed the mission from a controlled operation into something far more real, a true deep space scenario. Inside the spacecraft, the atmosphere changed immediately. Before the signal dropped, the crew had already begun documenting what they were seeing. Christina Koch described the moon not as the gray object we're used to, but as a surface filled with deep brown tones and extreme contrast between light and shadow. These weren't just observations for curiosity, they were part of a structured imaging effort, with astronauts working in rotating pairs to balance operations and data collection. One handled spacecraft systems, while the other captured high-detail imagery of the surface. But once the blackout began, everything shifted. There was no more communication with Earth, no real-time instructions, and no safety net. The crew had to rely entirely on their training and onboard systems. This wasn't just about staying calm, it was about executing precise operations under isolation. Every decision mattered, and every action had to be correct the first time. What makes this moment so powerful is not just the silence, but what it represents. For decades, human spaceflight has depended on constant communication with Earth. Even small missions rely heavily on ground support. But here, that connection was intentionally removed. The crew experienced what future astronauts will face when traveling far beyond the moon, where communication delays or complete loss become normal. And that's where the real story begins. Because this hour of silence wasn't just a dramatic moment, it was a carefully designed experiment. An experiment that reveals NASA's true objective behind Artemis II, and why this mission is far more important than it first appears. What looks like a communication blackout is actually the most important test of the entire mission. The goal was never just to orbit the moon, it was to simulate a condition where astronauts must operate completely independently. During the blackout, Orion systems were pushed into full autonomy, meaning navigation, life support, and environmental controls had to function without real-time oversight from Earth. This wasn't theoretical testing in a lab, it was happening in deep space, in real conditions. One of the key objectives was to evaluate how well both humans and machines perform without immediate support. Data from the mission shows that the spacecraft maintained stable operations throughout the blackout, confirming that its systems can handle long-duration missions. Life support systems continued regulating oxygen levels and cabin pressure, while thermal controls ensured the spacecraft remained within safe temperature limits despite the harsh environment of space. These results validate years of engineering designed specifically for deep space missions. But the technology is only half the story. The human factor is just as critical. Outside Earth's magnetic field, astronauts are exposed to higher levels of radiation, and their ability to think clearly under pressure becomes even more important. During the blackout, the crew's decision-making, communication within the spacecraft, and overall performance were closely monitored. This provides valuable data on how humans adapt when they are no longer connected to mission control. This is where the mission shifts from a lunar flyby to something much bigger. The conditions experienced during Artemis II mirror what astronauts will face on future missions to Mars. Unlike missions near Earth, where communication is nearly instant, Mars missions involve significant delays. Astronauts won't be able to ask for help and wait for an immediate response. They will have to solve problems on their own, in real time. By successfully completing this autonomy rehearsal, Artemis II proves that both the spacecraft and its crew can handle that level of independence. It shows that deep space missions are no longer just a concept. They are becoming operational realities. And that leads to the next question. If we now know humans and systems can function this far from Earth, what does that mean for the future of exploration? The real impact of this mission becomes clear when you look at what it enables next. Artemis II is not the final goal. It is the final test before humans return to the lunar surface with Artemis III. But more importantly, it lays the foundation for missions that go far beyond the moon. This is where the mission shifts from testing limits to expanding possibilities. One of the most critical achievements was validating Orion's free return trajectory. This path uses the moon's gravity to guide the spacecraft back toward Earth without requiring major propulsion corrections. In simple terms, it's a built-in safety mechanism. If anything goes wrong, the spacecraft naturally loops back home. Confirming this trajectory in a real mission adds a significant layer of reliability to future deep space travel. At the same time, the mission demonstrated that long-distance navigation and communication systems can operate effectively at greater distances. Even though communication was lost during the blackout, the spacecraft successfully reconnected once it emerged from behind the moon. This proves that the system can handle the transition between isolation and reconnection, which is critical for missions that will experience repeated communication gaps. But the biggest shift is psychological and strategic. For the first time in decades, humans are not just visiting space, they are preparing to live and operate beyond Earth's immediate reach. Artemis II shows that astronauts can handle isolation, that spacecraft can function independently, and that deep space missions can be executed with confidence. This changes how we think about exploration. The moon is no longer the destination, it becomes a stepping stone, a place to test systems, refine procedures, and prepare for longer journeys. Mars, and possibly beyond, becomes the next logical step. And perhaps the most important takeaway is this: the biggest barrier to deep space travel was never just technology, it was uncertainty. Artemis II reduces that uncertainty. It replaces doubt with data and theory with real-world results, which brings us back to that silent hour behind the moon. It wasn't just a moment of isolation, it was proof that humans are ready to go farther than ever before. That moment behind the moon wasn't about losing contact with Earth, it was about proving we don't always need it. Artemis II shows that humans can operate independently, think clearly under pressure, and rely on systems designed for deep space. This mission turns exploration from something experimental into something achievable. So now the real question is, when humans go even farther, will Earth still guide the mission, or simply watch from a distance? If you enjoyed this video, don't forget to like, share, and subscribe for more updates on space exploration and scientific discoveries. Your support truly makes a difference and helps this channel grow. Thank you for watching, and see you next time.